So do you want to unmute? Do you want to unmute? Have you unmuted? Yeah.
It's unmute.
It's unmute. Okay.
It's unmute.
Oh, okay. Thanks for coming, and let's just get this seminar started. It's our pleasure to welcome today's speaker, Emiko Hiyama, from RIKEN and Tohoku University. So a little bit introduction about her. So she actually very nicely prepared the slides about her background, so that the young people here can know those information. But I just very kind of formal thing. Just point out that she got her PhD at the Kyushu University, right?
Yes.
In Japan in 1998. And then just jump right now, she is the group director for field body system studies at RIKEN since 2017. And then she's a full professor at Tohoku University since 2021. Okay, there's a lot of things between that. She might just quickly go through for you. And I would just say that she has a broad research interest focusing on field body quantum systems, but then that covers several areas like hypernuclei, also low anti-nuclear physics. We are here interested in the hadronic physics. Okay, like she actually started with endoquark, all those things, heavy quark systems, and also cold atom systems. Anything that can fall into the field body system, I think she's interested in. So you're welcome to talk to her afterwards. And other than that, I will just let you take away. Yeah.
Thank you very much for the nice introduction, and thank you very much for inviting me to give a chance in this seminar. So can you hear me behind? Okay, good. Thank you. So then with that microphone, I start to give a talk. Okay. So then before having the seminar, so let me introduce myself. Okay. Maybe you may know this is the map of Japan, and Japan has two islands. And this is the Kyushu Island, and this is Shikoku Island. In this long island, you can see here is also there is a Tokyo and capital here, and this is a small spot and Hokkaido. Easy. Okay, I will use it. Yeah. Okay, is it okay?
Yeah, that's good, but there's one which you cannot.
Yeah, I try to do, but just so that it is difficult to and pick up my voice. So therefore, I want to use this microphone. Okay? Yes. Okay. So then around here, so that I was born in Kyushu Island, and here is this city is a focus city. It's my hometown, and here there is a Kyushu Island, and I got a PhD at the Kyushu University. And then after having a PhD, I moved to Keike as an associate, research associate, and I spent here 4 years. Then after that, I moved to Nara Women's University, and then here I spent time for 4 years as associate professor. And after that, I moved to RIKEN as associate chief scientist, and I spent time for almost 8 years there, and then in 2017, I moved to Kyushu University as a full professor. And then after that, and 3 years ago, I moved to Tohoku University as a full professor. And then now, I'm teaching the physics here, and also at the same time, I have my own laboratory at the RIKEN as a field body system in physics laboratory. And then this is the picture for my member. You can see it is me at the RIKEN, and it is the RIKEN's member. And she is my secretary, and he is a guest researcher in my lab. And I have 4 postdocs, and also he is a PhD student. And also he is a French person and Pascal Menon, and he is due in the root called atomic physics, and he is a permanent permanent staff. And also at the Tohoku University, I'm PI in this nuclear physics laboratory, and I have currently to have 2 associate professor and 1 assistant professor. And also, and I have my PhD student like this. Okay, this is my self-introduction. So then this is my outline of my talk. And after introduction, I shall talk about the 4-neutron system and also hydrogen 7. And finally, let me conclude. So then let's begin. And maybe you may know that the lightest isotope is hydrogen. So then this is the experiment data, and the neutron is the lightest nucleus you have a bound state, and the binding energy is a -2.2 MeV. So now we have a question. What is about the 2 neutron? And then we know we have no bound state, but we can add it 1 neutron and then many neutrons. And the extreme limit is a neutron matter, it's bound. So then we have a question. How many neutrons makes bound? Maybe in the 2 neutron may not have a bound. But what about the 4-neutron system? So theoretically, for instance, Stephen Piper calculated the 4-neutron system using the AV18 potential using the green function modeling current method. And he suggested that there would be possibility to exist a 4-neutron system as a resonance state at 2 MeV above the 4-neutron breakup threshold. And then maybe you may know that in 2016, at the RIKEN factory, they reported to have observed data of a tetraneutron state. So then they reported the energy is about it. That means now we have the 0 MeV, which this means the 4-neutron breakup threshold, and they reported to the energy is a bound region to the resonance region. So then, now this is a theoretically important issue motivated by this observed data. Namely, can we describe the observed 4-neutron system using the realistic interaction? That is our theoretical question. So then, after or before the recent observed data, and then we have some several results from cell research. So this is a positive result. That means so these two authors say that the resonance could be tetraneutron state, could be the resonance state, and begin with is like this using the non-Gaussian model calculation or quantum mechanical method calculation. And also, the other author said and reported not positive, not negative. That means that this author used a non-coherential model calculation, and also they used the N3LO potential, and also this is their calculation. That means that they factorize to this N2 body interaction, and this part is twice of this interaction, and this is energy with respect to the 4-neutron state. And if they multiply twice of this interaction, and they have a bound state for the tetraneutron state. But once they decrease that is factorization to the 1.0, then the energy is going up with respect to the 4-neutron threshold, and then became become so wide. Then finally, they have this result. That means the gap in the energy is around the 7 MeV about this threshold, and the gamma is around 4 MeV. That means that this is so much higher energy and broader width than this observed data. Then also, I calculated and the 4-neutron state motivated by this observed data, but we have negative result. So I introduced my result. But first, let me explain my method for this calculation. So in order to solve the cumulative problem very accurately, we use the Gaussian expansion method, which is a kind of the variational method using the Gaussian-based function. So this method has been developed by Kyushu University group and including myself. And this method has been applied to the hydration calculation of the various 3 and 4 systems such as exotic or three exotic molecular system and three unformed nuclear system and so on. So then let me explain more about my calculation method. And we usually use the relativity variation method. And then we obtain the eigenvalue E and eigenfunction psi. And here it's found that this total wave function in time sectors is the integral basic function defined by this equation. And that this rate variation principle leads to the generalized matrix eigenvalue problem. So then in this case, we should calculate the matrix element of the Hamiltonian and overlap matrix element. Then next, by solving the eigenstate problem, we get the eigenenergy E and unknown coefficient C. So in this way, we use this kind of method. So then more in detail for simplicity, and I explain about in the case of the three-body system. So in order to solve a three-body Schrödinger equation, then we use a three kind of Jacobi coordinate like this. And here is the Hamiltonian, and this part is the kinetic energy, and these are the two-body composed potential. And this potential is corresponding to this part, and also this part is corresponding to this part, and this three part is this part. And the wave function is expanded as the sum of the three channels of the Jacobi coordinate. And for the each channel is described as a spatial part and spherical harmonics for this small r part, and this is the capital R part. And for each and the channel is described as a small r and capital R coupled to the J5. And this C is a coefficient, and this C is determined by diagonalized Hamiltonian. So then for the especially the spatial part, we use the Gaussian-based function, and here is just a range. And then, and in the case of range part, we take the geometric progression like this. This is the first term of the geometric progression, and this ratio, and n is the number of the base function. These are the parameters. And then after taking this and range parameter to the geometric progression, then both the short-range correlation and exponential rate help simultaneously and produce accurately. And this is also the explanation for that in the case of the three-body system. But if we solve the four-body step, then we can just add it to one more Jacobi point. And if we try to solve the five-body problem, and we can add one more Jacobi point like this. And then using the and also after calculating the matrix element, then so with the eigenstate problem, we get the eigenenergy E and the unknown coefficient C. So then, in order to show up the accuracy in our method, in 2001, and we performed the benchmark test calculation among the 7 different two-body calculation methods. Okay, so that means that we use an AV8 realistic interaction, and we solve the bound state of the helium-4 ground state. But in this case, we use only two-body interaction. So this is a result. You can see this is the name of the two-body method. So this is the Paget-Jacobi method. And this is our result of my method, which is the Gaussian expansion method. And third one is stochastic variation method. And fourth and hyperspherical harmonics and green function multiplier and local Gaussian calculation and so on. And this is binding energy of the helium program state. And you can see that our results are good alignment with each other. And also we calculated distance of helium-4 alpha particle, then you can see our result with agreement with each other. And also we show up the two-body NN correlation function, and you can see just a straight line. That means our result are with agreement with each other. So in this way, for the ground state of the four-body system, we have the same result. So then even myself, I can provide the very forward bound state in high accuracy. So, however, so you see, that's our result at the same time, at this time, this is the expanded data of the helium-4. Then the only two system and our result is done by the expanded data. So then we needed some sleeping force. So then, in order to reproduce the data of the alpha particle, then we use just at that time phenomenological sleeping force so defined by this equation, just for two-phase Gaussian potential. Okay. So here, in order to reproduce the data of the helium-4 ground state, we need to the three nuclear force to isospin is 1/2 step, because to distinguish proton and neutron, we use that isospin. And now we define the proton part in the Z component of isospin plus 1/2, and neutron part is minus 1/2. Then in the Z component of the three nuclear system, and now 1/2. Therefore, in order to reproduce the data of the alpha particle, and the sleeping force of this part is the isospin part in 1/2. Then this part is the core part, and this is just for the attractive part. And in this case, in order to produce the binding energy of alpha particle, and we need attraction is minus 0.4 MeV. And then this is our result for the alpha particle. Then we see that, and the ground state is good affluent data, and also second zero ground state. Also, our result of good affluent is. So then, now this potential can be applied to the 4-neutron system. However, we should be careful about the three-body force, because in the helium-4 case, and isospin part and 3 nuclei is 1/2. However, in the 4-neutron system, it's the total isospin of the 3 nuclei is 3/2 step. So therefore, we need to the T4 3/2 but we have no idea how much attraction we need for the distributed system. So therefore, in order to study about the 4-neutron system, then we decided to use the same form of this helium-4 sleeping force. So this is our case. Okay. In the case of the core part is just fixed. However, attractive part is just a parameter. So then we should adjust so as to reproduce observe the 4-neutron system. Then, as mentioned before, 4-neutron system might be resonant state. So therefore, we should get the energy form. So therefore, the 4-neutron system, and in order to get the form, then I use the complex scaling method, which is one of the most powerful methods to get the energy form directly. So that to mean that I use this the basic function is like this, and for the range parameter scale into this, and then I scale into the high theta, and theta is just parameter. Then after that Hamiltonian, and then we can get energy for with the same parameter theta. Then with respect to the theta, then this is just an example of the complex scaling method. And the continuum state is moving like this with respect to the theta. However, if once we have a resonance state like this, then resonance state should be stable with respect to the theta. So then, and then from this we can see just a resonance state. Then in this case, the energy is measured from the 4-neutron breakout threshold. Then in this case, the energy is 6 MeV. And this is the imaginary part. Then decay width is correspond to the gamma over 2. Therefore, in this case, we have -3 MeV, then gamma should be 6 MeV. So in this way, we can have energy for using the complex scale method. Okay?
So it seems like you have 4 different calculations with different rotation angles.
Yes.
What is the motivation for that? What is the motivation?
Because from now, and I want to have this one. What do you mean? Here. Why so just so I have several calculation. Because just I want to show up to you that so the different state should be stable with respect to the theta. But so the continuous state is moving.
Okay.
Is that exact?
Yeah, but there is some dependence still for the random forward.
Of course, but if it's just with that would be fine. Okay, so then this is the result for the energy trajectory for the J equals 0 plus 10. So I cannot so. Do you know how to erase this part?
I kind of read Japanese, so there should be something here. Just, yeah, which one?
You can just click on the chat. Yeah.
Click on chat. The top is...
so is it because of chat, you'll go away? Okay.
I see.
Okay, so then so the energy, so this is energy trajectory for the J equals 0 plus 10, and then changing W1. Okay, so just let me.
I need to click on it.
Please.
It's freezing.
Freezing. How should we do?
You click on the slide.
Click on.
You click on zero.
Click, but I cannot do that.
Yes, just clicks on it. So sometimes it just freeze. Yeah, now it's working.
Cute.
I wonder.
I see.
So,
Thank you very much.
Okay, so let me again say, okay, for this, what is the W1? It's a W1 is the attraction of the three body force. Okay, this is the free parameter. Then from now, I change this W1 and I show up the energy trajectory for the 4 Newton state. Okay. Yeah, here it is. Okay. And then this is the sort of energy with respect to 4 Newton breakup structure. Okay, 0 to 4 something. Okay, and this area is a bound state energy region, and the experimental energy region is so like this, and the bound region to the just to and 3, 4, and so then, in order to produce this area, then I need to the minus 36 for the W1 to the minus 30 MeV. And then also I can change the soda in the value of the W1, and then this is the soda in the resonant region. And then if the soda this and the W1 value is becomes so smaller, then the energy trajectory is to become so upper with respect to the 4 Newton breakup threshold, and also to the minus 16 MeV now and the imaginary decay width becomes so larger. And in order to show more clearly, I shall show you the another here it is. And this part is just the value of the W1. And this is the energy with respect to 4 Newton breakup threshold. And this and the red line is an experimental energy region. Okay. So in order to reproduce this experimental data, then we need the minus 36 to the 30 MeV. However, if we have a smaller value of the W1, then the energy is also going up with respect to the 4 Newton breakup threshold, and the decay width becomes so wider. Like so then, you can see that so in order to reproduce the data of the 4 Newton state, we need a W1 should be minus 36 to the minus 30. And also on the other hand, so that in order to reproduce observed band energy of the alpha particle, then the W1 should be minus 2.44 MeV. And we can just compare with this attraction. Then, in order to reproduce that data, attraction is 15 times stronger than this one. So now we have a question. This W1 value for the T for 3 half is reasonable or not? So to check the disvalidity for the 3 body force, we calculate the energies of hydrogen 4, helium 4 with isotopy 1 and lithium 4. Okay? And in the case of lithium 4 and hydrogen 4, this is the experimental data. And you can see this is ground state to minus state, And here, this one is the lowest threshold. Then with respect to the lowest threshold, this ground state of this hydrogen 4 lithium 4 is just a resonance state, and the decay width is around 5 MeV, so broad resonance state. Okay. So then I calculate that this equal 4 nuclei, and this part is a W1 value, and this is the H. And then this is the lowest threshold, and if we use the W1 is minus 36 to 30 MeV, then we have very strong bound state for this part. Okay. And then if we go to this way, and it's just unbound. Okay. And then from this calculation, and then we use this value to produce the value tetrameters. Okay. We have some binding energy in this point. This result is inconsistent with the data of A4 nuclei because this J4 minus 2 minus state of A4 nuclei should be resonance. So then conclusion is following. So in order to reproduce the data of 4 neutron system, unlikely attractive driven force is required. And after my calculation, also the Duer calculate the same potential as mine. And so also he factorized about this in Emiko. And so if so that he has factorized for something like that, then they have a very strong binding. Okay, and this zero means zero energy is a 4 Newton breakup threshold. Then and he weakened the strength of factor. Then there's also an energy ball is coming there and it is appear. So that means there's also, and from this fact, he concluded no hope to existence as a resonance state for the tetrametron state. And also recently, he and Chris Green calculate the tetrametron state using the hyperspherical harmonic method, using the every potential, which is the same as mine. And also they calculate phase shift like this, and you can see the very small and phase shift. Then from this part, they conclude no resonance state. So this is the summary of the 4 neutron state, and some also had a positive result. But after that, so that I calculate this 4 neutron state, but we have a negative conclusion, and also using almost the same and then interaction, and Duer and Higgins also have the same conclusion, that means negative conclusion. However, last year, so that this is a nature paper, and just recently experimentally, and one peak near the 4 Newton breakup threshold, and the cross section has been evolved. So then we have a question. How do we interpret this experiment data scientifically? Then this year, we published a paper together with Limantas and German, and then in this calculation, mainly Limantas calculated. Okay. So then we calculated this reaction cross section using several kinds of interaction. And here is also our calculation. Okay, and we try to think about this part. So then we calculate only interaction, the multi-neutron and current and to the low potential, then you can see that we can have such peak. And also we could include the 3 force, but almost the same peak. That means the 3 nucleon force effect is so small. Then from this peak calculation, we interpret this peak emerged as a consequence, the final interaction among the 4 neutron system and the 4 neutron in helium 8 projectile. That is our conclusion. Okay. And then to understand the 4 neutron system in more detail, and the 4 neutron system, we can add a proton to this, and this is the hydrogen part. And also we can add it to one triple cluster to this part, then this is the hydrogen cell. Okay, so this part is the Newton number 6 and the proton is 1. It's a kind of a heavy hydrogen atoms. So then now we have a question. Can we understand hydrogen 5 and hydrogen 7 with an interaction so vacuum force? Okay, And then so we we published a paper in this physics week, and I shall talk about this part. So as mentioned before, the lightest nuclear to have a bound state is just a neutron in hydrogen atoms. And also we can add one neutron, and this is the triton, and we have one bound state. And also we can add one neutron, and this is hydrogen 4, and this is a very unstable and broad resonance state. And also we can add one more neutron. This is hydrogen 5. And almost 20 years ago, they observed this hydrogen 5 as a resonance state. And according to this experiment data, they observed the energy is 1 MeV above the triton plus 2n breakup threshold, and decay width is around 2 MeV. We call this nucleus as a super heavy hydrogen system. And then after this observation, and also there are similar experiment data for the hydrogen 5. This is a list of experiment data, and this part is energy. It's also almost the same, around 2 MeV above the triton plus 2n breakup threshold. However, you can see that this is the decay width, and decay width is a variety, and it's dependent on the experiment. And then actually in 2017, we have a new data on the hydrogen 5. Alan Uzma reported the experiment data on the hydrogen 5. And also, and the energy is similar. It's around 2 MeV above the triton plus 2n breakup threshold. However, they reported gamma with a so wide around 5 MeV. So in this way, and then the case experimentally, the decay width is strongly dependent on the experimental data. Okay. And also about the hydrogen 7. Okay. And also 20 years ago, that this experimentalists indicate existence of the hydrogen 5. However, they did not report any energy and decay width. And after the 2008, Hiyama et al. And observed the hydrogen 7, and according to their experimental data, they measured the energy is around 0.5 MeV and decay width is very narrow. So if we have a very narrow decay width at a low energy like this, maybe we could have a heavier hydrogen isotope, maybe and hydrogen 9. So, and what is the limit for the hydrogen isotope? Probably hydrogen 7 or hydrogen 9. Also for this meaning, it's very important to think about hydrogen 7 calculation. So then this is the theoretical calculation historical overview. And so far, Tohoku et al. Calculate the hydrogen 5 and the hydrogen 7. And she used the group of energy potential with framework of the hyperspherical harmonic method. And according to his calculation, she reported the energy is 1 MeV above the triton plus n threshold, and in the case hydrogen 7, she reported to have a resonance state above the 3 MeV above triton plus 4 n threshold. However, so she calculated energy with bound state approximation, so therefore she didn't give decay width for this requirement. And after that, Aoyama-san, Itagaki-san also calculated hydrogen 7 using the ALT calculation, and so they reported to have a resonance state for the 4 MeV above the triton plus 4n breakup threshold. And recently, the Chinese group also calculated hydrogen 5 and hydrogen 7 using bound shell calculation using the central information. Then the energy and the decay width of the hydrogen 5 was predicted to be the 1.4 MeV and the gamma is 0.5 MeV. And also in the case hydrogen 7 case, and the energy is around 2 and 3 MeV above the triton plus 4n breakup threshold, and decay width is around 100 keV. So then this is the experimental situation, and a few years ago at the RIKEN factory, this reaction was being done and the analysis is ongoing. Now we are waiting for the new data on hydrogen 7. So, And from this situation, it is timely to calculate the hydrogen level to obtain the energy and decay with theoretical. So motivated by this situation, we study the hydrogen level structure within the framework of the Triton and 4N fiber reform. And we also discuss on energy and decay width of the hydrogen 5 within the Triton plus 2N 3 by 4. So then this is my framework and hydrogen and 7. I take the Triton plus 4N 5 by 4. And then also and for the hydrogen 5, and then I take this 3 by 4. And then for the Triton plus neutron potential, there is large degree of activity because we have only several data for the phase shift of the Triton and TN part. So then, so my collaborator, Iman Saskas, calculate the forwarding system for the hydrogen 4 and lithium 4, and they try to calculate energy for like this. And also he calculated phase shift analysis like this based on the forwarding calculation. And after that, and he constructed Triton neutron for two-body potential so as to fit this theoretical value. And then so that he constructed two Gaussian range potential, and also they exclude the 0s orbit like this. However, even if we use this Triton neutron potential, and it was difficult to reproduce the hydrogen 5 experimental data. Therefore, I decided to introduce a phenomenological three-body TNN force to obtain the energy trajectory. But this is origin of the breaking effect of the Triton core. Okay. And here is this V0 and V3 is just a parameter, and this parameter is fixed. That's what to reproduce the data of the hydrogen 5. However, we have a question. Which experiment data of the hydrogen 5 should be fit? Because as mentioned before, this is a list of the experiment data, and energy is okay. However, in the case of the decay width is strongly dependent on the experimental data. So then I'm not sure which experiment data is reliable or not. So therefore, we decided to calculate the hydrogen 5 as a 5-body problem using several heuristic interaction. So then this is the total energy of the hydrogen 5, and then you can see that this energy is around 2 MeV with respect to the TNA breakup threshold, and the gamma is around 2 MeV. So this result is not dependent on an interaction and flow. So therefore, we decided to use this result as a quotation mark experimental data. But the interesting is this experimental data is very close to this experimental data. So then I shall show you the our theoretical result of the hydrogen 5. Okay. So then we take several types of the three-body force of the TNN. Okay. And this black line is B3 is 6 centimeter, and then this red line is 7 centimeter, and the blue line is 8 centimeter. And this value is just correspond to this V0. Okay. So then from this part, and the blue line is just so enclosed experimented. Here is this blue is just potential mark experimented by my colleague Hiyama's fiber calculation. And this green line is just experiment data taken in 20 years old and collision force experiment data. So then both data are just across this B3 and the 8 centimeter. Then we take this parameter. Then if we this potential parameter, and what is the energy for of hydrogen 7? So this is our result. Okay, and then this blue line is a result by the hydrogen 5. And this black line is a result of by and hydrogen 7. Okay. So then if we use this value, so the V0 is 2.5, then energy of the hydrogen 7 is around 9.5 MeV, and the gamma is 3.5 MeV. So then our energy of hydrogen 5 is much higher than with respect to the described plus 4N black box threshold and much broader begin with. However, if this hydrogen 5 resonance state is a very narrower resonance state, then quickly hydrogen 5 is an energy becomes so lower, and sometimes we have a bound state. So in this way, our result is a very strongly dependent on the energy of hydrogen 5. Okay, and this is a summary of the hydrogen isotope. And according to our calculation, and in the case hydrogen 4 and hydrogen 5, our result of good agreement with experimental data. Also, this is we put on the hydrogen 6, so maybe no experimental data. And then this energy of the hydrogen 6 a little bit so above the hydrogen 7, and then this is our result. So then from this summary, maybe we think about hydrogen 7 should be end of the hydrogen isotope again. Okay. So let me summarize. In the case of 4-neutron system, and theoretically, it is difficult to have a resonance state with an realistic force. So to interpret recent data on the SOP near the 4-neutron breakout threshold, and we calculated this reaction. And so we interpret that P a consequence of the final state interaction. And also we calculate the hydrogen 7 system, and because motivated by this reaction, and we calculate this system. And assuming that this energy should be 1.9 MeV and gamma to 2 MeV for the hydrogen 5, then our calculated energy became with the hydrogen 7 about the energy 8 to the 9 MeV, and the gamma is 3 MeV. However, energy and the width of the hydrogen 7 is strongly dependent on the energy position of the hydrogen 5. So therefore, maybe it would be very helpful to confirm the energy port of the hydrogen 5 and experimentally. So if our calculation hydrogen 7 in good agreement with future experiment, and it would be difficult to have a resonance state of tetraneutron state. Okay, so thank you for the attention.
Very nice talk. Any questions about the audience people? Yeah. Okay. So
Yeah, I have a question.
I'm a little confused that you say that the nature approach that these signals for neutron system, you are saying that theoretically it's really hard to get it with the three-body force, but you also do some calculation with the three-body force to get this resonance peak and say that the three-body force is not important. So that means the peak in the experiment is not for neutron system.
Yeah, that is our conclusion. Because even in the system, we can reproduce this peak. It's a final state interaction, right? So that is why this is not any resonance. Just in order to show us this is evidence, then just simply we calculate.
Okay, but that's I'm not quite sure, but for the resonance calculation, I think maybe the model speeds of the could have some rules. For example, if you do not include enough information in your business, you may lose something when you try to describe the resonance. So have you tried to explore if you reduce or increase your model space, does that will have some influence on resonance?
Okay, yes, so that is quite interesting. So then for the tetraneutron state, then I use a enough basic function. And if I reduce some basic function over some combination of the configuration mix, then any energy fall and so quickly disappear. So therefore, in order to get the resonance state, yes, we need to choose some more enough basic function and as well as enough configuration. The under more configuration. So therefore, always we should be careful that how many and basic function, also how many and configuration we need. Right? So then if we put hydrogen 7, and then in order to get the energy and core, then so that we include so the and enough and configuration mixing and angular momentum also spin combination. And as well as the spin bend and basic function.
It sounds like you have done like the convergence test on all these calculations.
That's right. So then always and I try to try and error many times.
So I'm actually interested in this the serial formalism here. If you don't have enough space, if you truncate the space, your calculation, what happens in those poles on the branch cut? Do they just get scattered around, or do they still align on the branch?
It depends on how many basic function we include.
Right.
Sometimes it's a no pole, but just all rotate, continuous just all rotate.
But they still align on the cut.
Yes, sometimes. Oh yeah.
Okay. Yeah. Yes. Any other questions?
Yeah, I have a couple of questions.
Like this final state interaction, is there any feature of the decay or something that can be measured that can help with theoretical interpretation?
So in this case, I don't know. I cannot say anything about it here. Just so that we calculated just a 4.
Right.
Yeah.
But yeah, depending how the experiment is carried out, there may be some information of how the state decays. What is the decay configuration?
Yes.
Where also this may be very low statistics. I don't know.
Yes. So this is so I don't know that maybe so that just I read it so that this nature paper, but so they didn't say anything. Just decay process. Just that they have some.
Okay. But sometimes you may calculate something in code and tell them what they should do.
Yes, you are right. Yes, right. For instance, also I'm interested in this Pentacock system, but there wasn't complete and they have the decay process, right? So then in order to see that about this picture, then we also theoretically we should have the decay process, right? Yeah. So that is also and I want to do that. But this time is just they so measure the just date.
Yeah, maybe I will comment. So that experiment, they use missing method. Okay. So they don't see any. But I think there is a schedule or I think proposal to do the experiment. Okay. With like this time we gave the form. Okay. Yeah, that's fine, but we've done it for Shinto again. The decay rate.
So that is a RIKEN experiment?
Yeah, I think it's a RIKEN experiment with the panel that's gathered.
Already this experiment, the project already approved at RIKEN?
I'm not sure if it's approved or if it's a plan proposal.
Okay.
But there is a plan to do it.
I see. I should check it.
So go ahead.
So one thing that I read in another paper was for probing the final state index. There were basically two options: either trying to calculate the spectral function and see how it looks with energy, and if it deviates from the traditional bright radar light chain, or time propagating it. So is it possible to do the can you calculate the spectral function?
Of course, yes, that's right. Once we have some resonance set, then we can have some wave function. In this case, usually we can calculate the response function. But this time, I cannot produce anything about the resonance set, right? So that is the thought point.
Yeah, okay. And then,
so Joshua, would you guys try to calculate response function? Calculation?
Not in mine, but Simon Law is it to get spectral functions. And then he showed that for final state interactions, it was for nitrogen 9 and helium 9, that as you create more of a scattering feature as opposed to a genuine resonance, you deviate from the bright radial light shape, and then that would lead to non-exponential decay and basically a smearing of your pattern and getting more of an actual final state effect.
So they actually happen.
Yeah. So in that case, I was just wondering if obviously time propagation is a hard thing in its own, but did you have any idea or any intent of trying to do like time propagation or studying more like correlations between some of the emitted particles like dineutrons or anything like that?
Yes. So once we have anything so that on the resonance state, something like that, then so we have anything, we have anyway, we have one function. So therefore, then we can easily and calculate the probability and population. Yeah. So, but then so that even for the hydrogen 7, in this case, we have very broad resonance set. In the case of broad resonance sets, it is difficult. So then, in this case, always we should have a narrower and the resonance set. It's a compound. Over bound state, we can do it. But the broader resonance set, it might be difficult. This is my.
Okay, so you basically lose the point of that.
That's right.
So he's asking about doing some time dependent.
No.
No.
No, currently no. But I'm interested.
But you do have all the frequency domain information. So
Yes, so yeah, so then
research information you can get all the time.
I think so. But maybe so it takes some time and also CPU time. So numerically it was a very hard task, right?
Yeah.
Currently, I do not think so, but maybe someone can do and someone can help me.
So for these young people, they grew up with this impression that current interaction is the interaction for nuclear physics. So do you have any? But then you see, like there's a lot of merits of doing phenomenologic interaction because it's easier to calculate, right?
Yeah.
But my question is, what about current interaction? People would ask you about theory.
Okay. Yes. This is so for me already all the calculation, right? So then recently, just last month, I changed my mind. That's why I started to collaborate the bomb physics. And so just 2 weeks ago, he visited my place in Sendai. Then we discussed each other. Then he teach me how to treat the current potential. Then I understand. That to me, and the next year, if you invite me, I will show you. You can see the current potential.
So do you see any fundamental difficulties in implementing?
Yeah.
Can I ask a question?
Any more questions?
Yes, I have a question.
Someone is sorry, I cannot
Can you speak louder?
Can you hear me?
Wait a minute.
Can you hear me?
No.
Can you hear me?
It's very small. And how should we do? And can you so speak out?
Can you hear me?
Wait a minute.
Yeah.
Can you hear me? No.
I can hear you, Udo. I don't know if she can.
But it is difficult for me to hear.
Can you just type your question because it's very hard to hear you clearly here.
Can you hear me?
No. Yes.
Can you hear me?
Can you can you tell me?
How do you read? Can you hear me? Can you hear me?
Voice.
Can
you hear me? No.
Let me take this. No, it's your computer. So you don't have this issue before. Yeah, it's the other side.
Udo, can you type your question
can you hear me?
in the chat?
Can you type your question in the chat? Yeah.
All right.
Please.
Can you hear me? Can you hear me? Okay.
Let me check this one. Check.
This is chat.
Yes.
Can you hear me?
No.
Can you type your question in chat? Maybe not.
Can you hear me? Can you hear me?
Yeah, he just keep repeating that.
Can you hear me?
We cannot hear you.
Okay.
It's too low volume.
Can you hear me?
No.
Can you hear me now?
Please type your question.
Can you hear me now?
No. It's just I can barely hear, like.
Listen. No, I don't know. What should we do?
Just wait. I mean, I just wait a little bit. I think you have. Do you have more questions?
Can you hear me?
Yes.
Can you hear me now?
Udo, can you hear me?
Yes, yes.
Okay, they cannot hear you. Do you want to tell me your question and I'll relay it, maybe?
Okay.
Can you ask the question?
Can you hear me? I have a question concerning your three-body forces. Namely, there supposed to be some quantum mechanical symmetries, the Efimov state for a three-body system, for example, in tritium or helium-3. Did you check on those? I saw that you checked on the binding energies, but nothing else. It was sort of a remark on passing. And I have another question.
Ask about symmetries of the interaction.
Yes.
Beyond the binding energy and the existence of Efimov states for these interactions.
Efimov, correct.
Yes, but whether you went anywhere farther than just values of the binding energy.
Okay, yes.
Okay.
That
was the question. Did you check on Efimov states?
Efimov states, whether you checked on Efimov states. No.
Another question about the quantum symmetry of a four-body system. If you have two paired neutrons, you have two bosons. What is the boson constant state possible? A bound state? What's the role of the exchange?
So boson condensate with two paired neutrons, whether such a state is possible.
Correct.
That will be done in the future. Udo.
Oh, thank you.
All right.